Lithium-ion batteries are commonly used today for their high energy density. Since batteries are usually used for handheld or portable devices like phones and laptops, we want them to be as lightweight as possible. And in order to do this, parts are made as thin or as light as possible. These thin or light coatings on the batteries are usually fragile, and the problem is when the battery gets damaged, a short can occur, and these shorts can spark and ignite the highly reactive lithium or the flammable electrolytes. Batteries can also heat up to the point of exploding due to the heat of the contents exerting pressure in the batteries. This specifically happens when they're charged or used for a prolonged amount of time. An example of this is the Samsung Galaxy Note 7, which caused a huge issue a few months back because of its battery problems. Batteries are made up of the cathode, anode, electrolyte, and a separator. In this research, thermal-triggered separators were made so that when they reach a specific range of temperature, a flame retardant is released. The structure of these thermal-triggered separators are shown in the top left corner of the slide, which shows a core shell structure of the microfiber. The most important part of this slide is the top right part, which shows the melting point of pure TPP and PVDF HFP, which is the coating of the electroshell. The TPP shows a melting point of 50 degrees, while the PVDF HFP shows a melting point of 150 degrees. This means that the PVDF, which coats the TPP at this point, will only release the TPP at around 160 degrees. A demonstration of what will happen when this temperature is reached is shown on the bottom half of the slide. So what makes this separator special is illustrated on the images shown on the chart. The top left image shows directly mixing TPP with electrolyte and its negative effect on capacity, which shows that more TPP equals less battery capacity. The bottom left image shows no direct mixing of TPP, the black line, versus 30% directly mixed TPP, the red line, versus the thermal triggered flame retardant separator, which is the blue line. This clearly shows the minimal difference between the no TPP and the thermal triggered flame retardant capacities. This means that the ones with thermal triggered flame retardants perform almost as if it had no TPP in the electrolyte. The images on the right demonstrate how effective the thermal triggered flame retardants are at quenching the fires. The images show the actual separator wetted by electrolytes. They show that at around 0.7 seconds after the fire starts, it's immediately almost quenched. While there's no patent directly claiming the TPP at PVDF HFP separators, this is the closest patent I could find. The claim of this patent is not specific to the TPP PVDF HFP separators discussed earlier. The patent here vaguely describes a common battery with a few additions. The description of the battery being claimed is that it has one or more cathodes, one or more anodes, and three phases that contain an electrolyte and around 3 or more flame retardants. It says nothing about the flame retardant being in the separator. So what can be done with this innovation? Lithium-ion battery fires are more complicated to put out than typical fires. As a result, responders that are not well informed about lithium-ion battery fires might be in danger. A lot of the current devices and technologies use lithium-ion batteries, and preparing for possible accidents becomes even more of a concern when every device has the capability to cause dangerous fires. And with the movement to the trend of electric cars, everyone has to address this problem. This is where the flame retardants come in. It won't prevent the battery in the device from failing, but when it does, it reduces the risks associated with its failure by putting out the fire almost as soon as it starts. So with that, the demand for this innovation will only get higher as the world moves towards a more battery-powered future.